This is the video introduction to experiment 3 for Chem 300. This is a neutralization titration. The goal of this experiment is to determine the percent of replaceable hydrogen, which is expressed as a percentage of KHP by mass, in an unknown sample. The titration that we're going to do is a neutralization or acid-base titration. KHP is a weak acid, sodium hydroxide is a strong base, so this is a weak acid, strong base titration. The reaction of interest you can see there. The important thing to notice is that the stoichiometry is 1 to 1, and we'll come back to why that's so important later, but 1 mole of sodium hydroxide reacts with 1 and only 1 mole of KHP. The indicator that we're going to use is a molecule called phenolphthalein, which is another weak acid. It has the property that it's colorless in acidic solution, pH less than 8, but then when the pH goes above 8 and really above 9.6, you get a nice pink color. This range, 8 to 9.6, is called the indicator transition range. The unknown that you're going to get will be in a little vial, and it's a solid powder containing some percentage of KHP. Just like you dried your KHP to constant mass, you're going to need to dry the unknown so that you can be sure that all that's in it is KHP and inert material. You don't want to be weighing any water in. The indicator transition range that I mentioned before is important to know because the equivalence point needs to match up with that range. There are two concepts here. There's the idea of the equivalence point and the end point. The end point is the visible representation of the equivalence point. The equivalence point just means you've added an equal number of moles of acid as base for a 1 to 1 reaction, or if it's 2 to 1, you've added twice as much, etc. We'll just consider 1 to 1. So at the equivalence point of our titration, we will have added an equal number of sodium hydroxide moles as there were moles of KHP in the flask. Mathematically, that's the equivalence point. Visually, what we see is the end point, and the difference between them is called the titration error. What we want is an indicator that minimizes the titration error. So we have a weak acid being titrated with a strong base, and so as you'll find out in lecture a little later, the equivalence point is going to happen at a pH a little bit above 7. We don't know exactly where without doing some calculations. What's important is that our titration endpoint is going to show up in that range, around between 8 and 9.6. Since the slope of a titration curve is always very steep near the equivalence point, it doesn't exactly matter if the endpoint shows up a little before or a little after the equivalence point. Since the slope is so steep, the pH is going to look essentially the same, and so that will minimize the titration error. I'm not going to go all the way into all of this, so your textbook, sections 10.2 for weak acid strong base titrations and 10.6 for indicator function will give you more information. For all the titrations we do, the general procedure is going to be this. You're going to make your titrant. You're then going to standardize that titrant using a compound called a primary standard, which in this case is KHP. And then you're going to use your standardized titrant to titrate the unknown and find the concentration of your unknown. So to make your titrant in this case, your titrant is going to be sodium hydroxide, and we're going to start out with a 50% weight by weight solution of sodium hydroxide. Whether we start with this solution or if we started with solid sodium hydroxide, either way, it's very difficult to control the amount of sodium hydroxide that we actually put in to our titrant. So you're going to measure out, not too exactly, about 5.2 milliliters of sodium hydroxide. And you're going to add this to a 1 liter Nalgene bottle. If when you measure, you put in exactly 5.2 milliliters of sodium hydroxide, after you pour out of the graduated cylinder, the sodium hydroxide is viscous, so some of it will stick. You want to rinse that out with distilled water and pour the rinse into the Nalgene bottle. If you pour in a little more, like 5.4 milliliters, you don't need to rinse, just rinse it out in the sink. Once you've transferred as much of your sodium hydroxide as you can into the bottle, you're going to fill it up to the shoulder, as shown in the bottom right there. That means there's about 1 liter in there. Okay. Now, all of this is very inexact for a class called analytical chemistry. And the reason is, we don't need to make it perfectly because we're going to find out the concentration of sodium hydroxide in that bottle in the next step. The way we're going to do that is by titrating KHP a known amount, with our titrant. So you're going to weigh about 0.8 grams of KHP, and you're going to have it in 3 Erlenmeyer flasks. You can also do a fourth and do what's called a burn, which is where you do it inexactly just to see about what volume your endpoint should be at. If you are confident in your technique, you can do 3 very good trials. You can do 4 very good trials. Either way. Once you have your KHP in your Erlenmeyer flask, you're going to add about 100 milliliters of water and swirl to dissolve. This takes a long time. Be patient. KHP just doesn't dissolve very quickly, but it will all go into 100 milliliters of water. You're then going to add about 2 or 3 drops of phenolphthalein indicator to the flask and swirl to mix that around. The phenolphthalein is going to be in these little dropper bottles, and they'll be at your bench. So now you're ready to start your titration. You fill your burette with your titrant, your sodium hydroxide solution. You put the Erlenmeyer flask underneath the burette, and you start dispensing. And what you're going to see is a pink color where the titrant stream is coming into the flask. And as you swirl early in the titration, that pink should just go away immediately. As the titration proceeds, the pink will take a little bit longer to go away. And so that's how you know you're getting close to the endpoint. At this point, you should start adding the titrant drop by drop, as slowly as you can mentally put up with. At some point, you may want to add a half a drop if you think you're really close to the endpoint. The way you do that is by letting the partial drop kind of get out of the tip of the burette but not fall, and then rinse it in to the titration flask with deionized water from your squeeze bottle. The reason that this can be done is that the total volume in a titration doesn't matter. It's also why we tell you to add about 100 milliliters of water to the flask. What matters is the number of moles of sodium hydroxide and the number of moles of KHP. You can add water at any point, as long as you don't dilute it so much that you can't see your indicator. You're not going to hurt your results. So as you go on, you're going to eventually reach a point where the pink color doesn't go away anymore with swirling. This is sort of the darkest endpoint that would be acceptable. The lightest endpoint that would be acceptable is where you can just barely see a hint of pink. As long as the pink sticks around for 30 seconds or so, you know that you're at the endpoint. Your data analysis is basically going to involve stoichiometry. So you're going to do roughly the same thing for your standardization and then for your unknown determination. So the stoichiometry is going to involve a few steps. So you're going to take your mass of KHP for the standardization. You'll take your mass of KHP that you put in the flask, convert that to the number of moles using the molar mass, and then you're going to multiply by the balanced chemical equation to find moles of sodium hydroxide that you delivered with the burette. So at the equivalence point, moles of KHP equals moles of sodium hydroxide, because this is a 1-to-1 ratio. The reason we use the mole ratio is that the ratio is not always 1-to-1, so it's always good to put it in the stoichiometry. Incidentally, this is the reason that you never, ever use the dilution equation, M1V1 equals M2V2, to analyze the results of a titration. It will coincidentally give you the correct answer when the mole ratio is 1-to-1. But in all cases when it's not 1-to-1, like in next week's experiment, you'll get the wrong answer. So once you have your number of moles of sodium hydroxide delivered with the burette, you can divide by the volume that you delivered and find the molarity of your titrant. Once you know that, you do your unknown determination titrations, and you do the same calculation in reverse. You start with the volume you delivered, calculate the number of moles of sodium hydroxide, multiply by the mole ratio to find the moles of KHP that were in the flask, and then use the molar mass to find the grams of KHP in the flask. But you're not done at that point, because you want to figure out, okay, of the total amount of unknown I put in the flask, what percentage of that was KHP? So you divide grams of KHP by grams of unknown sample, total sample, and that gives you, and multiply by 100, and that gives you a percentage. That percentage is what you're going to report as your answer. Some percent of KHP in the unknown. Your accuracy grade is going to depend on how close that number that you report is to the true number specified by the manufacturer in their assay certificate.